morning, everybody. We will go ahead and get started with our March webinar today. Today we're going to be discussing solvent dyes, and we will go ahead and get started. And so just as I do each month, I'll record this, and so all of those in attendance and those who have registered but couldn't make it today will get the link to the recording as well as the PDF of the presentation. I understand it's tough to make all these, but if you ever want to do that, make sure that you get the information, just go ahead and still register so that you get all the link as well as the PDF. So if you have questions, please use the chat box and I'll address them at the end of the presentation. So I'll go ahead and get started. I'm going to go off screen here. And so as I mentioned, we'll talk about solvent dyes today. Part of them, they are part of the colorant world. Just kind of a fun fact that there are about 9,000 in total of dyes and pigments that are used or have been used. Some of them may not be active anymore in the industry. So there's a lot of choices out there. If you haven't figured out by now, the intent of these is to help you identify the appropriate colorant to use in all of your applications and making sure that they match up for all of your needs as well as your color. So solvent dyes will be certainly, as the name implies, they are going to be soluble in some sort of organic solvent or non-polar type of a media in here. They will offer that nice transparent color to your end applications, even at especially at low loadings. As we've talked about before, unlike pigments, they will completely dissolve as long as the polymer and dye chemistry are matched up appropriately. They will completely dissolve to be able to provide that nice transparency. From a physical property and traits of them, solubility and transparency, those are the key in here. So it's always good to match up. The first thing is to match up the solubility with the appropriate polymer in here, because you don't want to have it look like a pigment if it's not fully dissolved into the system. So then it just looks like a pigment, and it potentially will give you a more hazy look to it. Heat stability, they tend to be very good with the higher processing temperatures. And again, this also is a chemistry related property in there. Strength, they're always going to have great strength, especially even at very low dosages in here. So you're going to get that nice high strength from it, as well as that clean chroma and hue for these areas. Light fastness and weather fastness, just like in pigments, these always are going to depend on the chemistry that is used for that particular color and dye. Oops. Some additional things to consider. We've already mentioned about suitability. In some cases, there might be a migration risk, especially if the polymer in use might be a more of a lower TG polymers. So it's always, you always need to be able to match the solubility and the polymer together. Pretty much they have great compatibility with plastics, primarily because of the chemistry of these plastics. We do see some really good performance in engineering plastics, as well as other amorphous plastics as well. I already spoke about fastness and stability, but one thing about exterior or UV fade considerations, just like in pigments, they will have a difference of reaction to UV in terms of fade. And if you're using multiple dyes within the color itself, um, just take note that there might be a change in rate of the two of the dyes in there. So when you have your initial color, it during the fading process, it could change color directions based on the rate of fade of that particular dye in there. So your end color could look differently in those intermediate ones. Mechanical properties, because if they are completely soluble in the polymer itself, there's not going to be any impact on those mechanical properties. Unlike with pigments, where they will maintain that physical solid structure throughout the polymer, that could induce some impact on mechanical properties. But as long as the solvent dye is properly dispersed and solubilized, mechanical properties should be fine. I'm a visual person, and so the next couple of slides, this slide and the next one, gives you a better feel for what I'm talking about with a pigment versus a dye. So pigments, there always is going to be a physical particle in that particular article or dispersion, whether that's a plastic dispersion or a liquid dispersion. So those particles are going to scatter, absorb, transmit, and reflect light. So you're not going to get the full amount of transparency that you can with dyes, because they do dissolve completely. So all of that light will be transmitted through the article to give you that brilliant color as well as that transparency. The other visual, obviously, is just the solution of them. Pigments are always going to be that solid particle, so they're just going to sit there and look at you, whereas the dyes will dissolve, and you can see right through them. Some other examples, seeing is believing is kind of where I like to look at things, and so I have a few examples of how that transparency of a dye in a real application area can be significantly different in here. So in this red space, solvent dye 135 versus a pigment red 53-1. Same amount of loading in this polystyrene in here, so you can see significant transparency difference between a pigment and this solvent dye. In the orange space, same idea here. On the pigment side, we used a combination of yellow 62 and red 53-1 that you saw in the previous slide to get to a similar orange color space. Still the same amount of loading in this application area, but significantly different in terms of color. When we get to the yellow side, because yellows themselves are light in color, they will have a better transparency when it comes to pigments, but still we can see a significant difference between the solvent dye, in this case a solvent yellow 93 versus a straight pigment yellow 62. That allows some interesting color developments and opportunities to take advantage of effect pigments. So this is a very simple formulation of a solvent yellow 93 and a iridescent gold mica in here. So this allows your article, depending on what you're developing, especially if it has curves or edges, to be able to basically get a 3D effect, color effect. And also with that 3D, you actually get essentially several colors to the eye. On the flat, you'll just get that transmitted color and transparency as the bottom of the screen shows. And then on the angles, as you're going around a bottle, for example, you start to bring in the effect itself to get another color or effect in your design. So in as far as the classes of solvent dyes that are typically used, there are three classes. Azo-based dyes, these show up primarily in the red and yellow space. Anthraquinone, we see those in the blues and the greens. They tend to have a little bit better, they have better heat and light fastness. And then metal complex or other specialty dyes are brought into the mix to be able to start to improve some of the deficiencies of the other chemistries in certain areas in there. Very similar to high performance azo pigments that were developed to improve on physical properties of the classical azo dye pigments as well. So these are also have the same idea to be able to identify where there is a hole in a property and come up with another approach to get that color space, but with improved properties. So a lot of these things I've already said here, so I won't spend too much time on this one, but they have a unique place in plastics, and bringing that high chroma, high transparency. Um, Also, they are very good, especially for those uh, engineering polymers. Um, and again, matching up the polymer chemistry to the polymer itself to be able to get that good solubility that you need. Because you need these in low doses to get that good color and strength and transparency. They are lower in cost to use because you don't need as much. Um, can't stress enough, they are very polymer specific. Um, and we already talked about the performance in terms of UV and exterior grades, so we need to match those up as well. And then the fade rate differences between these also have to be considered. So we've used this chart many, many times, but it's really good to really key in on this one. So for a pigment, we say that about 75% of the performance comes from the chemistry of the pigment. And then that performance can be manipulated or shifted in one direction or another by the choice of finishing step that can be used for that particular product of pigment in there. So there's several knobs that we can do on the pigment side to get the properties that we're looking for once we have the chemistry for the color. On the dye, 100% of the performance really comes from that dye. There is no finishing or surface treatments that are used on these, so it all comes from the dye. Makes it a little easier in your selection process in there because there's just a few key things to be able to hone in on to be able to match your needs to the available products and chemistries. That brings us to this chart that we use a lot in here. Again, looking at your selection process, certainly color and effect. We saw some interesting ones earlier with bringing in effect pigments to go with that great transparency of the solvent dyes. But certainly you have to make sure that it's the right polymer, the right heat stability profile that the dye will see, matching those up. Interactions with other things in the formulation, this is where I talk with not necessarily an interaction, but if you're using a mix of dyes, that UV fade rate will be different between one dye and another. So that might be part of that selection process. From a performance perspective, it's not a particle, so there isn't a dispersibility except for that solubility part of it. Particle size, again, we get that because we get that transparency through the dissolution. And of course, compliance comes in every aspect when it comes to plastics to make sure that your formulation meets the required compliance areas, depending on where that article will actually go. Cost value, I also talked earlier about because these are used in such low amounts, there's a good value in use for using solvent dyes. Some application areas that typically can use, if you so choose, solvent dyes, engineering and commodity plastics. I spoke about those earlier. Polystyrene, polycarbonate. These are key ones that having a good transparency is key to the end product, and how it's received in the industry, or in basically to you and I as we move down the shelves and pick our products. And end markets, consumer good and packaging, key, automotive, construction and electrical housings, and anything that really does need to be transparent and bring those very colorful, intense aesthetic properties to your end product in here. Other specialty uses, thin film colorations, fibers and yarns are also using some of these solvent dyes to be able to get that very vibrant color at low usages. Some tips, again, matching the application to the dye for processing temperature, as well as the polymer polarity. Key, those are the two keys. If you take nothing away from this webinar, those are the two key ones to match when choosing your dye. And those turn into the potential for migration and blooming if it's not properly and 100% dissolved into the polymer. Of course, can't forget about regulations. Sometimes that's the first on the list to be able to look at. So, we see this one a lot. It's going to be a balance. You're not going to get everything that you're looking for. But in this particular case, some of the things that we typically talk about when we're talking about pigments, those come off the table for your listing of attributes, because it is just the chemistry that's going to dictate the performance. So still having your list of musts, wants, and nice to haves is key in getting your right selection of the solvent dye. Some examples. So I was able to bring to you today some case studies, as well as a little bit of a comparison of some of these dyes and what they can and can't do for you. So I talked about the types of chemistries, azo dyes being one of them. Again, these are typically found in the red and yellow space. These are going to have the lower heat stability profile. Again, all of these statements that I have here are generalizations for the category itself. Medium light fastness, but they do have some applicability. Okay, I think I came off. Applicability in two key polymers as well. These are going to be a little bit more cost efficient than others, but the kind of the statement is you get what you pay for, so to speak. These are going to be a lower price, but they're also not going to give you the high performance properties that others will. Anthraquinone, again, we talked about the blues and the greens. Some reds fall into this category as well. We start to see a higher heat stability profile for these, as well as their light fastness and an extended polymer suitability for these as well. Paranone, these are, they're still a subset of the anthraquinones, but these also provide a little bit better performance. Oranges and reds can fall into this category. They're going to have the higher heat stability and light fastness, and then again a bigger set of polymer suitabilities that we have. So of all of these three, they will be the high performance versions of these solvent dyes. And then I spoke about earlier the metal complex. These were developed to fit the holes that exists in the other areas. So you see a lot of hue range of various hues. Heat stability can be variable depending on what they were designed for, what hole they were designed to fill. You might get a lower heat stability, but a better light fastness kind of a trade-off in there. So from a polymer side perspective, polystyrene, azos are okay because they do bring you those transparent colors in there, but got to pay attention to the heat stability profile that's required for the application. The anthraquinones, that's where that comes in, especially if it needs to have color fastness, where there's higher heat in the application or UV type of scenario that you might see. Polycarbonate, this because of the nature of the polymer itself, it's going to require the dyes that have the highest heat resistance, and which is not the azos, unless you pair it up with stabilizers to help with that the heat profile. And then PMMA and ABS, these are some other areas where dyes fall into good suitability for these areas, depending on what you're looking for. Some case studies that are used in the industry. So I'm not really telling you anything new, but it's always interesting to see it again. In this case, taking a look at transparency packaging in polystyrene and ABS. Here, consumer packaging, so they're looking for clear color. And so both types of the main chemistries will be applicable here. But again, the temperature and UV response has to be considered when selecting an azo dye versus an anthraquinone dye. Again, based on that performance outcome, what you're looking for. So it's that balance of properties and chemistry to be able to make sure that you select the appropriate dye for the actual end product. So, for example, from a cosmetic packaging aspect of it. So think going down your aisles in the drugstore or the grocery store, and you're looking at these nice clear but vivid colors for packaging. More than likely there are solvent dyes in those, and that's what they're being used for, that clear film or packaging area to be able to illustrate what is inside the container. For example, if it's a product that has an effect pigment on the inside, you want to be able to see that movement of that effect color through the bottle in here. So that's where the transparency comes in. Of course, you could always put the effect pigments on the outside as well. Automotive, both on the inside and the outside, depending on what you're trying to achieve in here. So again, choosing the right chemistry for the application areas is important to be able to do that. Your car taillights is key. That's going to always be the Solvent Red 135 because it is that higher performance in chemistry, gives you that clear red color to it. So just keep that in mind as you're going down the road and looking at the taillights of the car in front of you, and think solvent red 135. Flexible films. These are films that are used for both signage and light boxes where there is going to be a light behind it. So you want to be able to have vivid colors as well as transparent in there to be able to get the message across and catch somebody's eye to look at that particular sign. These are also used in theater, concerts, and everything else like that, where you want to be able to change the lighting color that you're putting onto the stage. That's where these types of films come into play. Um, Certainly, the choice of it really depends on the processing of the polymer itself, as well as the end use in there. So in this particular example, where we're using the lighting, the color filmed for lighting, the polymer, the solvent dye needs to be able to withstand some pretty intense temperatures from the light itself to be able to provide that color for the show, if you will, to be able to do that. And then, from a sort of that stained glass effect that is very popular, these colored sheets need to be able to be placed in sort of that stained glass window effect, give that transparent color, but also can withstand certain amounts of that UV exposure, so they don't fade away. So this is just an illustrative slide to reinforce what I've been talking about as far as that haziness with respect to a pigment versus that clear, vivid color with respect to solvent dye. So different application areas to give you another visual comparison of what you can and can get with pigments versus solvent dyes. So in all areas, if you're looking for something that's very clean, very clear, vivid, solvent dyes are a good way to go if your application, of course, and your other properties can tolerate some of those the solvent dyes. Information can be found on our website. We have a very good product finder in here, so the ones that are available from Sudarshan, you can just go up to the product finder and select plastics and dyes, and you can get more information about each of these dyes along the way. So we talked, the previous slide showed that, one category, one brand of dyes are the Solvaperm dyes. These tend to be our more higher performance solvent dyes. In there, they contain the chemistries that fit that that kind of generalized term in there. From a standardization perspective, we're always testing them in polystyrene. A listing in in the website can give you this information as far as the chemistries that are available, as well as the polymer suitability, the heat stability, and other information that you can find useful in your selection for solvent dyes. This one is the second part of the blues and the black and green. Pastasol, that's another brand in the solvent dye area. They have a fairly unique perspective to the solvent dyes in that they provide an edge fluorescence in there, and so what that allows to do is at the edges where it tends to be a little bit thicker from a polymer perspective, it glows to be able to give that. So these aren't by definition fluorescent solvent dyes, but they give that edge effect or edge glow or light piping is another way of doing it, just by the way the light captures those thicker edges to be able to give you that look. Uh, Three of those are in the Hostasol brand area. And then the polysyntherin dyes, these are more specifically tied to fiber and film application areas. They do have several um, chemistries that show up in the other brands as well, but these have more of a pronounced usage in those types of application areas. And again, so you see the variety of those chemistries that are available and the polymers that they go with. So at this point, I'd like to open it up to any questions that you might have.